Hello everyone, welcome to Inspire Mathematics. Today I will share my NBHM PhD interview experience with all of you. And this interview was held in 1st March 2024, and this is an online interview through Google Meet. And when I join, when I there are 6 professors. One of them is Gurmeet Boxi from Punjab University, and there are and one faculty, one sir from either Pune, and many more. I cannot remember all of them. And when I joined, first they asked me to give my introduction. I give my introduction, and then they asked me the preference on which I give my interview. I told that I prepare abstract algebra, real analysis, and topology. Then one of them start with abstract algebra. First, they asked me this question. They told me to give an example of a group in which Z20, Z7 and Z3 both can be embedded. And I told Z3 direct sum Z7. This is the group Z21, and in which both Z7 and Z3 can be embedded. Then they told me to give an example of a non-abelian group in which both of these group can be embedded, and I told Z21 direct sum S3. This is a non-abelian group and in which both Z3 and Z7 is embedded. Then they asked me to give an example of uh, group of order 21 which is non-abelian and in which both Z7 and Z3 can be embedded. Then I told that here 21 can be embedded. 21 can be written as 3 into 7, and 3 divides 7 minus 1, and we know a theorem. If G is a group of order PQ and P does not divide Q minus 1, then G is a cyclic group. Then G is cyclic. G is always cyclic and isomorphic to ZP cross ZQ. And but if order of G is PQ and P divides Q minus 1, there is a non-abelian group. There is a non-abelian group of order 21. Order PQ. And this non-abelian group can be constructed using semi-direct product. I told this theorem, and I told this type of group can be constructed using semi-direct product. Then they asked, do you construct this group? I told that I cannot remember in this time. I cannot construct this in this time, but I know the concept how to construct. And this construction is quite laborious, and you can see this in Damitton foot. In Damitton foot, there is the construction. You can see this, and then they said they satisfied with this. They don't need this whole construction. Okay, this construction is not no one can give this construction is an interview or okay. So they satisfied with this what I told, and they moved to the next question. The next question was they told me to define group action and give some example, and this is easy, and you can see this in any book, for example say Damitton foot and any other book. This is very easy. And next they asked me this question. This is a very nice question, and they asked me, on a finite abelian group, does there always exist a non-trivial automorphism? And when they ask this question, I am stuck. But first they give me hint. So what is the simplest abelian group? I told that this is Z2, non-trivial, obviously Z2. And okay, then on Z2, okay, on Z2 they ask that there is no non-trivial automorphism. Yeah, on Z2 there is no such non-trivial automorphism. Now I told this, then I use on a finite abelian group. Then I remembered every finite abelian group can be written as, if G is a finite abelian group, then I can use the fundamental structure theorem. Fundamental structure theorem. What is fundamental structure theorem? Zn1 direction Zn2 direction Znk, where each nk is greater or equal to 2, and this n1 divides n2 divides n3 and so on, nk. Okay, I have to use this structure. If one of this n1 is not equals to 2, then suppose Znk is not isomorphic to Znk. Suppose this nk is not 2. So in Znk I can define an automorphism Znk to Znk, which is phi x equal to x inverse. Okay, since this nk is not equals to 2, then I can define this. This is a non-trivial automorphism. Okay, then if I define psi with the help of this phi, which is psi x equal to psi x1 x2 dot 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 xk equal to this x1 goes to x1 x2 and this phi x, this xk, sorry, this is sorry, this is this n, this here I assume this ni. Okay, here I use nk, so this is ni. Okay, this is ni, sorry, this is ni, because here I use k. Here phi xi, this xi goes to phi xi, and all the coordinates are fixed. Then you can easily check that this is a non-trivial automorphism, since this is non-trivial, because this ni is not equals to 2, because if ni is equal to 2, then the only automorphism from Z2 to Z2 is identity automorphism, because in Z2 if I define this x goes to x inverse, this x inverse is x. Okay, so this, since this is not, this ni is not equals to 2, so this is non-trivial, so this is also non-trivial automorphism. Now if now they give me the hint, when what can we do when all these ni's are 2, that is, if if G is isomorphic to Z2 cross Z2 cross Z2, then what can be done? And then I start, and they told me to they told me to prove with the simplest one. The simplest one is, if G is isomorphic to Z2 cross Z2, then they told me to work with this Z2 cross Z2. Okay, and now this Z2 cross Z2 is K4, and if we write this Z2 cross G, I can write this 0 0 1 0 0 1 and 1 1. Okay, and you know that the automorphism group of K4 is isomorphic to nothing but S3. Okay, so we can get many non-trivial automorphism from Z2 cross Z2 to Z2 cross Z2, and this proof is very easy, and you can find it again in Damittan-Foot, and this is very easy. And okay, and when they ask, when I prove this, they asked me to prove this in interview, and then with their hints, I proved this automorphism group of Z2 cross Z2 is isomorphic to S3. And then I remember that the result, the automorphism, if G is isomorphic to Z2 cross Z2 cross Z2, then the automorphism group is, then automorphism group of, and this is n times. Okay, suppose this is n times n times direct product of Z2. Automorphism group of G is isomorphic to GL2 Z2. Okay, sorry, this is GLN Z2, and I after proving for Z2 cross Z2, I simply use this result. The automorphism group of G is isomorphic to GLN Z2, and they don't need the proof of this, because this proof is not quite easy as Z2 cross Z2. Okay, then they are satisfied with the answer, and they asked me questions from real analysis. Then one of the teacher asked me questions from real analysis. First they asked to define the differentiability at a point and give some example. I give the definition and give example, sin x, cosine x, and all of them. And okay, now they asked me the domain of differentiability, in which domain they are differentiable. I told that this is differentiable on whole of R, and now they moved to this question, second question. They asked me to give the example of function which is not differentiable at exactly one point. And first, then I told them, can I give the example graphically? Then they are very happy with this proposal, and I draw the graph like this. I draw a graph from here to here. Say this is 0 to this is a, okay, and this at that point, at this point, if it is 1, at this point this function is not differentiable, and in whole domain this function is differentiable. Here I define the domain is 2 comma 0 comma 2. Then they ask me to give an example of a function which is defined whole of R but is not differentiable exactly at one point. With the help, and I do this with the help of this function, and I simply extended this here and here. then this function is defined on whole of R, and this is the point at which this is not differentiable. Okay, now they ask me to give an example of function which is not differentiable at 2 points and which is not differentiable at countably many points respectively, and all of these functions are continuous. They also ask me to give the example of continuous function which is not differentiable at 1 point, 2 point and countably many point. For 2 point, I construct the graph same with the same uh, concept. If this is whole of R, if I define it at whole of R, this is 2. At this point this is not differentiable, at this point this is not differentiable, and I yeah, I extend it like this. At this point this is not differentiable, at this point this is not differentiable. This is the function which is not differentiable at exactly 2 points. And for countably many points, I draw simply this graph, and in this side, okay, like this, and I name this is 0, this is 1, this is 2, this is 3, sorry, this is 3, this is 4, this is 5, this is 6. Okay, this function is not differentiable at all integral points, not differentiable on z. Then one of the professor told me that how can I construct this, how can I write the definition of the function. Then I told that if this is the point 0 0, and if this is the point say 1 comma, so this is 1, so the 1 comma a, then I join the straight line, then the u then the equation of the straight line is the definition of the function from third bracket 0 to 1, and like using this concept for all of this line segment I can define this on whole real line, and then they are satisfied and they moved to the next question. The next question is, does there exist a function which is everywhere continuous but nowhere differentiable? Again I told about that sawtooth function, and then they told that no need to explain this function because this explanation is quite very difficult, and this is given in the book of Rudin, principle of mathematical analysis. If you can see this in Rudin, but they don't ask the explanation for this. I just name this function, name the function, and then they asked me, one of the professor asked me to give an example of a function which is C1 but not C2, and I give this example. I give the example of x cube by sine x square, and x is not equals to 0 and 0 if x is equal to 0. This function, and I define it on third bracket minus 1 comma plus 1, or you can define it in whole of R. Okay, and then I give this example. Then one of them are surprised and they asked me, how can you give this example so fast? Then I told that I can change this exponent, these two exponents, such that I can construct such function. Then they asked me to explain, then I give the whole explanation how this function is c1 but not c2, and there are some related question like how this sign in here I have to use the limit x tends to 0 sine 1 by x. This does not exist. I have then to prove this function c1 but not c2, I have to use this limit. This limit does not exist. And in interview I told that this limit simply does not exist. Then they asked me to give the proof of this also. They asked me to prove this, how this limit does not exist. Then I give two sequence that tends to 0, but the limit of that sequences as n tends to infinity are different, so this limit does not exist. Okay, they are very happy when I give the example of this function so fast. The average duration of interview was 50 minutes, and when with this question the interview was around 45 minutes or 46 minutes, and then they told me uh, am I am I comfortable with the series of function or sequence of function. And I told that, oh yes, I know this. And then they asked me the questions. Then they asked me to define pointwise convergence and uniform convergence, and I give these definitions. And then they give this problem. And first they asked me to find the pointwise limit. The pointwise limit is if x belongs to open interval 0 1, then fn x this okay, sorry, close 0 open 1, then limit n tends to infinity x to the power n is 0. This implies limit n tends to infinity, whatever be this part, x to the power n into log of 1 plus root over of x by 2 is equal to 0. Okay, and if x is equal to 1, this log of 1 plus root over of x by 2, at this if I put 1, this is log 1, and which is 0. So the pointwise limit is gx equal to 0. This is the pointwise limit. Then they told me to whether this sequence of function is uniform convergent or not. Then I try to find this mn. All of you know that what is this mn. This mn is supremum of this fnx minus fx. Okay, and all of you know that if this mn tends to 0, then this mn tends to 0 if and only if the sequence of function is uniformly convergent. I try to use this theorem, but I try to find this mn, but I can't find this. Then they ask me, can I remember some result? Then they give me the hint, can I remember some result? And then I told that I cannot remember. And they told me, do you know some theorem like this? If fnx is equal to x to the power n into fx, where f is continuous, then this fn is uniformly convergent if and only if this f1 equal to 0. They told me, can I remember this result? Then I told that yes, I can remember. And then they told me, with the help of this result you can easily tell that this sequence of function is uniformly convergent, because if this is a, because here what is this f1? This f1 is log of 1 plus root over of x by 2. Okay, and this fx is this, and f1 is log of 1 plus 1 by 2. And what is this? This is nothing but log 1, which is 0. So with the help of this you can tell this. And they they give me enough hint in all the interview period, and they are very helpful. Okay, so in the whole interview they give sufficient hint to solve these questions, and finally they are satisfied with my answers, and I am selected for NBHM 2024 NBHM PhD scholarship of 2024. Thanks for watching. If you like this video, please comment and subscribe my YouTube channel. Thank you.